Hello everyone, welcome to our webinar today. I am Ayhan Akray and I work as a technical consultant at Allplan Competence Center for Infrastructure. And I will try to explain how to design a bridge with automation in Allplan Bridge and Allplan Engineering. Before we dive into details, let me give you a brief overview of what you can expect from this webinar. We will be seeing the complete design process from Allplan Bridge to Allplan Engineering. In other words, we are going to see the process from beginning to the end. We will be exploring various design challenges that bridge engineers often face, such as varying road geometries and element dimensions. Our aim is to provide you with practical solutions that will make your design process easier. Throughout this session, we will delve into creation of specialized libraries, handling varying access data, and merging geometries to achieve results. We can see how this defined element can be used parametrically. Also, we will integrate a real terrain model into our project and performing excavation works. And to top all of it, you will be able to see how you can create detailed deliverables and present your project with a beautiful renders, even with the virtual reality. We have included a question and answer session at the end of the webinar, so make sure you take a note and note down any questions that come to mind during this presentation. Without further ado, let's get started. Now, I would like to start with introduction by giving you a brief overview of automation in bridge design parametrically. Parametric design is an approach that allows us to create designs driven by parameters or variables. It brings efficiency, flexibility, accuracy, and innovation to bridge design. Firstly, automation through parametric design saves time and effort by streamlining the design process. We can automate the repetitive tasks and define links between parameters that can allow the design to adapt automatically. Secondly, parametric design offers the flexibility in handling varying road geometries and element dimensions. We can create specialized libraries that can be easily modified, or they can also be reused. Thirdly, accuracy is ensured throughout the design process. By defining the links between parameters, any changes made to one element automatically adapt to the related elements. It can eliminate human error and ensuring the precise and reliable designs. In conclusion, automation through the design enhances efficiency, accuracy, creativity, ultimately delivering the exceptional bridge designs. That is why we wanted to show you and remodel Shusha Arch Bridge as an example, highlighting how you can overcome the challenges posed by varying road geometries and cross-section geometries. This bridge is a real example, and detailed project design is successfully completed by Yüksel Proje. The total bridge length is 424 meters, and the single-lane railway is transported. It includes a 280 meter span and 51 meter high concrete covered steel arc. The first and last two spans will be constructed with balanced cantilever method, while the remaining decks will be constructed with the scaffolding system as custom placed post-tensioned, and this scaffolding system will be supported by the arc. The columns supporting the balanced cantilevers have the height of 51 meters. The Allplan Bridge main workflow is first defining geometries, merging geometries and connecting to them each other parametrically, assigning tendons, and synchronizing the whole model with Allplan Engineering. Firstly, let me explain the general workflow. On the left hand side, there is a work tree consisting of geometry, result, and analysis. Today, we are going to focus on geometric definitions. In the structure tab, the general workflow is like this. First, you can import terrain. Then, you can import or define road data in Access tab. After that, you can define your cross sections. This type is like a library. In other words, this is like a formula to shape how the cross section would look like. And in the variation type, you can define any kind of variation to be used either in axes, tendons, or structural members, any type of member. And lastly, the last one is structural members, where you can finally assign the cross sections that you defined in cross section tab with custom variations. Firstly, you can start by importing digital terrain model, as known as DTM. You can now use parametrical referencing of bridge substructure like abutments, piles, foundation, and piers to automatically generate terrain access. After you import the terrain access profile can be generated automatically, and structural members of bridge can be referenced parametrically to this terrain access. You can see any object can interact with the imported terrain. After importing the DTM, we need to define axes. There are different kinds of axes, and I will explain them in detail, but first we need to define the main axis, which will be a reference for top of rail elevation. Axis information can directly be input manually, or it can be imported from another project or from BIM+. For manual entry, you can just simply use the axis tab and can adapt any road geometry here. There are also types of axes attaching to this main axis. You see let me show you. You see the orange one is called accompanying axis, and it's parametrically linked to main axis. What I mean by parametrically is when you change the main axis, the accompanying axis would also automatically change based on the criteria. By criteria, you can link the profile data to any formula, table, or even to terrain. You see, the accompanying axis is following the terrain. For example, this is the main axis, okay? And this accompanying axis is linked to the main axis with variation. You can see, for example, you can assign the height of any cross section to check your cross section height. And even this terrain can also be linked to the main axis to create an accompanying axis. This is also an arch axis that we will use this later to assign the arch. This is another main axis, and this is transverse axis. The cross-section tab can be used for defining cross-sections. The general workflow of this cross-section is straightforward. At the start, you are giving two axes in each direction like that. You can use the cross-section tab above to create parametric lines and points with just a simple clicks on the lines, and program will also suggest you to use these commands. Any kind of shape can be created, such as this complicated superstructure, geometry of box girder. Please keep in mind that you can define any kind of variable to these lines and points, then these can be linked to the variation tables or formulas. Creating libraries is a powerful tool in parametric design that allows us to overcome design challenges and ensure efficiency in our bridge projects. By developing a library of predefined cross-sections, we can easily integrate any kind of cross-section into our designs, regardless of the varying road geometries and element dimensions. Any kind of shape can be created, such as this complicated superstructure, geometry of box girder. Please keep in mind that you can define any kind of variable to these lines and points, then these can be linked to the variation tables or formulas. Creating libraries is a powerful tool in parametric design that allows us to overcome design challenges and ensure efficiency in our bridge projects. By developing a library of predefined cross-sections, we can easily integrate any kind of cross-section into our designs, regardless of the varying road geometries and element dimensions. Imagine having a comprehensive collection of cross-sections at our disposal, specifically tailored to handle different road geometries and element dimensions. This means that no matter the complexity of the project, we can design an appropriate cross-section and incorporate it into our bridge design. The versatility of specialized libraries lies in their ability to adapt to project-specific requirements. We can create libraries with a wide range of cross-sections, including various shapes, sizes, and materials. Furthermore, specialized libraries enables us to explore different design possibilities. We can experiment with various cross-sections, analyzing their structure, behavior, and performance in relation to specific road geometries and element dimensions. This empowers us to make informed decisions and select the most suitable cross-section for each unique bridge design. The integration of any kind of cross-section with varying road geometries and element dimensions become a reality through the power of automation. By defining links and constraints within our parametric design software, we can ensure that selected cross-section adapts to the changing road geometries and element dimensions. Any modification made to the road geometries or element dimensions will automatically propagate through the design, maintaining accuracy and consistency. In conclusion, creating specialized libraries in bridge design is a game changer. It provides us with the ability to integrate any kind of cross-section, regardless of varying road geometries and element dimensions, ensuring efficiency, flexibility, and innovation in our designs. The variation tab is used to create and define tables or formulas for describing the variation of variable parameters of cross-section along the bridge axis. The variation of certain cross-section dimension along the axis is defined by creating a table in tables, or you can just use a formula with mathematical expressions like that. For example, here you can define a lot of variations here, even in table formula or even in mathematical expression like that. The variation is not directly used by themselves, but they have to be linked to the assigned member so that it can be parametric. Until now, we have defined a terrain, axis, cross-section, and variations. With the structure members assignment, a model can be created now. There are 6 types of structure members. For this bridge's geometrical modeling, only 4 of them will be used. The topic of this webinar doesn't include the analytical calculation model. Therefore, analysis can be a topic for another webinar. For the analysis, there is also possibility for decks and connection as a structure members. Now, I would like to begin with the girder assignment. A girder member can be referenced to the axis and superstructure. Arch and trapezoidal foundation of this bridge can be created with a girder type of structural member. The construction of this bridge is a complex process that involves different methods for different spans. The first and last 2 spans of this bridge will be constructed using balance cantilever method, as I stated. Moving on the other spans, they will be built on scaffold that's supported by the arches and utilizing the post-tension method. When we examine the superstructure of bridge, we encounter a challenging geometry. This complexity arises from the variable concrete thicknesses and the heights of anchorage areas. A girder type of structure member can be created with many types of cross sections linked with different variations. Let me show you in the software. So you see, we hide the structure members. Let me open them, the cross sections, and these are the structure members. When you open the structure members, you see the girders are assigned to the bridge. The superstructure is composed of one element, and it has properties of stationing, cross sections, and variations. When you double click the cross sections, you can find a table, and you can see in each different station you can assign a different cross section that was defined before. And you see a diaphragm here, and girder span here, and even the anchorage different area. When we zoom in the girder, let me close this terrain. When we zoom in the girder, you can see a different cross sections in just one girder. And also, with the variation of this girder, you can assign any kind of variation here. For example, the bottom thickness of the height is changing, you see. Bottom height, sorry. And the tendon spacing can be changed in here as well. These kind of variations can be assigned here. And for another girder example, the majority of bridge is carried on arc element, which also gives the bridge its name. The main structure of the bridge is made of structural steel, and let me show you where it is. Here, and is covered with concrete to reduce maintenance and repair costs and labor. You can model this arch path steel by just defining one section. You see, these lines can be parametric, and their width and the thickness can be changed based on the variation table. Additionally, you can define the cross sections by using the link girder feature and connect to them to the reference point on assigned section. As since these cross members are connected to station points on arch, their lengths can also be parametric. A girder can also be assigned to accompanying axis. For example, if this was an accompanying axis, this would also be parametric to the main axis. Here, even with one simple cross section, you have possibility to create this arch member that's linked to the accompanying axis that's connected to the main axis, like that. This arch is also a one member, and it still can also be another member that can also be connected to the foundation. These are all coming from one cross sections. For example, this arch cross section is parametrically defined here, and the steel one is also different in the same parametric lines. We can also see a girder can also be assigned to the transverse axis as well. Here, a trapezoidal geometry of foundation is assigned by using just one cross section. When we go to the 3D model, you see this is just one girder assigned by this transverse axis at P1. Moving on, the other structure member is pier. As you can see, the important element of bridge is the pylons, which are 51 meter high. When designing such columns, it's necessary to consider both feasibility and aesthetic importance. This can lead to numerous iterations, especially in dynamic calculations and architectural concerns. Additionally, the precise connection of these columns to the superstructure and foundation, as well as the avoidance of reinforcement clashes, are the great importance for ease of construction and safety. This column is modeled with a single pier element and consists of 4 different cross sections. A single pier element can consist different cross sections, just like the girders, like that. For example, this is a P1 pier. You see this has the same interface as the girder, and different from the girder, this has this can be attached to the main axis, and it can has a local stationing, and you can assign different cross sections just like in the girder, of course with the variations. You see the width here is changing, and this width is coming from this table. This is changing from 3 and 3/4 and 1.5 meter. When it comes to the other columns, since these columns are directly connected to the arch, they need to be modeled with great precision. Here we can model these columns with pier or link girders as well. Additionally, the assigned columns can be copied and used on other axes as well. For example, we modeled this column, just a simple rectangular one, and the other piers and the other columns are copied from this one. Just their connection to the main axis is different. And by link girder, I mean, I will tell you in detail later, but by link girder you can connect to them to main axis to the arch axis parametrically. Lastly, I would like to mention about these link girders. The cross members can be assigned with link girders, and you see here in the picture there is a parametric points in the cross section that the link girders can be linked to them. Also, since these parametric girders are linked to these parametric points, they are parametrically connected to the width of arch or height of arch, and when you change them, as you can see here in the video, they can change parametrically as well, the cross members. And for the abutments of the bridge, it can be so easily to model 3D volume elements with bodies. When modeled with bodies, a structural element can be merged, divided or subtracted from each other with new Boolean functions. Here, originally, this abutment is consisting of many body members as known as solid members, and you see, for example, the front wall is a main member, a foundation is connected to them, and the wing walls are subtracted from the front wall as well. So you can use the tree modeling and Boolean functions here as well. Under the bodies you can see the assigned bodies, and if you right click to the one member and Booleans function, you can see what applied to that section, and by just cancelling to just cancel, you can just simply delete these functions. Okay, and when you rerun the project, the Boolean functions is gone. And the main skeleton of art is made of steel, and it's connected to the trapezoidal shaped foundation with a large anchor. We can model the trapezoidal foundation and observe the interaction between the reinforcement inside it and the structure steel by modeling them. You see here the structure steels are modeled as a different cross section, and the large anchor is also modeled so that the reinforcement interactions can be seen after that. And for the tendon assignment, in the cross section of relevant girder, you can define grid points to assign tendons. The grid points can be variable and parametric so that a challenging tendon geometries can easily be assigned with just one table. The logic is like an array function, and vertical and horizontal distances between each tendon can be parametric, like in this model. So here I modeled a simple tendons to that section. You see these are all different grid points, and as I said, you have two different directions, U direction and V direction, and these can also be parametric by defining a new variation from the table. These are all different grid sections. For example, if we want to see the tendon top parametric, we just simply assign, and in the cross section, in the girder of this cross section, we can see the tendon top variation is assigned here, so that the assigned tendon here can be changed parametrically. For example, we can observe the tendon here is inclining because of this variation. Here is a video showing how grid points can be used and changed parametrically with just one table. As I showed in the previous model, the tendon top is attached to the variation, and also in the diaphragm regions you can define a same variable, and under the variations you may assign your variation table just for that tendon, and you can attach them parabolically, linearly, and finally in the structure members variations you can assign this formula to the girder. You see all sections have the same formula changing. For example, in this 70 region it's 0.15 from the top, but it's changing in the 50 region. And when we want to change the, for example, table, it can automatically change and apply to the model, but you have to recalculate it to see it. You see, the distance from the top is changed with just one table, and these variations can be applied to different tendons as well. And lastly, all these structure elements and tendons can be parametric each other, as well as they are parametric with the axis. For example, say your axis is changed due to the revision, and your bridge can instantly be adapted to the new axis in just minutes, as in the video. Now our bridge model is completed, and say if we want to transfer to the all-plan engineering, it can be parametric. And what does that mean? If you change anything in your model in the all plan bridge, it can also be parametric in all plan engineering as well. So after your model is completed, you want to detail and you want to transfer this data to all plan engineering, and here is the video is showing how you can transfer them parametrically to all plan engineering. So all the models, all the paths, all the elements are transferred to the all plan engineering so that you can make cross sections, make some detailings, and make some deliverables in here. All the sections you can play with. And you can also create your own sections as well in here. And what you can do after transferring to the all plan engineering, you can additionally import a terrain point to create terrain model, and you can do some excavation works here with Python parts already built in the software. And after that, you can assign a reinforcement to the models, the structure members and girders, and even create with them some deliverables for your construction project. After that, you can even synchronize it with Twinmotion for visualization. Even you can use virtual reality with your model. Let me show you that part. And firstly, you may want to model the terrain and conduct an excavation for yourself. Assume that you have a DEA file that contains coordinates like X, Y, Z representing points on the terrain. You would like to import these points into the all plan construction and terrain module, and you can automatically mesh them, and after that you can convert them into solid element. Let me show you a small example how to do that. For example, you have imported your points like that, and in the construction segment find the terrain module, and you can automatically mesh and optimize your points like that. And after that, with this function, you can create a new solid to work on. Here you can say to convert into solid, then you click your terrain model, then you can even state your base elevation like that. So it can be created in new like that. For the excavation part, with the solid terrain and transferred bridge elements from all plan bridge, you can then use the excavation pit feature under the terrain module to apply excavations at desired geometries with desired inclinations. So let me show you that in the model. Now you have your solid terrain and you have your bridge elements from all plan bridge. As I said, under the terrain module, under the excavation pit, you can use array-shaped cut and fill feature. And what does that mean? This creates a Python part with the selected geometries. You have to draw this by referencing the foundations, and even you can reference the roads you may want to excavate, so that you can have your excavations and views. And these Python parts can then also be edited to your desired inclinations. For example, if I want to change the relation of these, I just simply put, and it automatically changes the excavation. Now, after the excavation, we need to detail our project. We need formwork and reinforcement details for the project. For detailing part, I will only give example for assigning reinforcements and prepare deliverables with them. For reinforcements, you can either assign them manually by using a reinforcement module in Bridge Construction tab, or you can assign them parametrically with All Plan Bridge. Any kind of shape and size of the reinforcement can be defined and placed, and after that they can be detailed for your deliverables. For placing reinforcement, you can also use All Plan Bridge's new feature of parametric reinforcement. Parametric reinforcement is a new way to define reinforcement that works both for code checks in All Plan Bridge and for detailing in All Plan Engineering. This feature can also work both ways, meaning if any assigned reinforcement changes in All Plan Engineering, you can also automatically update the reinforcements in All Plan Bridge as well as for your code checks. You can place longitudinal, shear, and torsion reinforcements with this feature, and you can also indicate the overlapping regions with this by the help of the predefined Python parts. After you prepared your formwork and reinforcement details, you can prepare a deliverables, and they can also complete the parametric with the elements you defined. You can take a cut from plan view, and you can also make a cross section and label your reinforcements, and you can give a dimension to them, and you can also get automatic quantity tables that can also be updated parametrically. You can have your individual company logo and many more here. Now you prepared your deliverables and some construction drawings, and you may want to visualize your model more. For this, you can use the TV motion synchronization. Under the construction tab and visualization module, you can use TV motion directing auto synchronization to synchronize your model. To do that, you can choose your import option, and you can directly link it to TV motion, like this. And it can automatically link what you see on the screen. And all you have to do is to click your important element and press F, and you see the exact model that you see in the model came here. And after you import it, you can add some mountains, some environment, some trains, railways, and even some boats and some excavation workers. And you can also import your excavated solid terrain, and you can change your model concrete materials like this. You can assign any type of concrete to your bridge by just drag and drop option. So you can do many more, and you can add some waters here as well. And after that, you can render, and you can create some beautiful renders in TV motion. And let me show you that. Hope you enjoyed it, and if you have something like this VR, you can even see this model in virtual reality by choosing this VR option. And let me just connect this and let's see the workflow. And yeah, here we are in the model, and you can see how realistic it is. The boats are going, you can see the train closely, and you can even change the time. See, let's go a bit afternoon. Yeah. And you can play with your materials. Let's see if you wanna change your concrete type. For example, this for your arc. Why not? You can even do like this. You can also change it back always. Most interactive design ever. And you can go to floor. Yep. And see what this guy is doing. Hi. You can walk around. And yeah, something like that. So yeah, that was the whole workflow. In conclusion, we tried to show you a comprehensive overview of all plan bridge and its geometric definition, merging of geometries and parametric design, tendon assignment, and synchronization with all plan engineering, even importing terrain models and excavation works, and reinforcement assignment and deliverables. After that, we showed you TV motion synchronization and even virtual reality. So we hope you find it insightful and look forward to assisting you in the leveraging these tools for your engineering projects. So for any questions of yours, we will be there to answer them gladly. So thank you for attending again and have a nice day.